The following material contains rigorous medical and physiological analysis. This content is produced strictly for educational and informational purposes for peers and students in the life sciences, and does not constitute individual medical advice. Traditional whole blood donation collects all cellular and liquid components in a single, unseparated pint. It relies on volume, drawing approximately half a liter of blood and relying on the laboratory to process the components later. Within that blood are platelets, tiny, disc-shaped cellular fragments produced in the bone marrow. Their primary biological function is to maintain vascular integrity through a process called hemostasis. When a blood vessel is damaged, platelets migrate to the site of the endothelial injury. They aggregate, binding together to form a temporary mechanical mesh that repairs the tear and prevents further hemorrhagic loss. This clotting mechanism is a daily requirement for specific clinical populations. Oncology patients undergoing chemotherapy frequently experience suppressed bone marrow function, while severe trauma victims face catastrophic bleeding. Both require continuous transfusions to survive. The primary logistical hurdle in transfusion medicine is the shelf life paradox. Extracted platelets remain viable for only 5 to 7 days. Unable to be stockpiled, this degradation creates a supply chain problem. Cancer wards and trauma bays exert constant demand against an expiring inventory. Modern medicine addresses this rapid consumption through Plateletpheresis, an automated filtration loop that separates specific cellular components while the donor remains connected to the machine. Sustaining advanced medical procedures requires transforming raw whole blood into a real-time, density-filtered biological resource. The extraction process requires extensive physiological preparation. Donors are instructed to consume heavy, non-caffeinated fluids to support their intravascular volume and to eat calcium-rich foods to build systemic mineral reserves. Baseline hematological thresholds are strictly enforced. To safely donate, the individual must present a hemoglobin level above 12.5 grams per deciliter for females and 13 for males, alongside a baseline platelet count exceeding 150,000 per microliter. This data table illustrates the pharmacological deferral system. Certain medications disqualify a donor, notably a 36 to 48-hour ban on aspirin and specific non-steroidal anti-inflammatory drugs. Aspirin causes the irreversible inhibition of COX-1 enzymes, effectively severing the synthesis pathway for platelet thromboxane A2. Without thromboxane A2, platelets lose their ability to aggregate. Pumping non-aggregating cells into an oncology or trauma recipient provides no hemostatic benefit. The mechanical demands of the machine also dictate physical requirements. The extraction relies on high-caliber venous access, specifically identifying the basilic or median cubital veins in the antecubital fossa to sustain continuous, high-pressure flow rates. Individuals with high cardiovascular fitness or regular weight training present improved vascular tone. This structural integrity prevents venous collapse during rapid apheresis fluid shifts. These precise thresholds are the result of decades of laboratory observation, establishing the baseline conditions necessary to extract viable cells safely. Enforcing these filters guarantees that the collected cells are functionally active upon transfusion, while actively protecting the donor's vascular and hematological health. Platelet apheresis utilizes an extracorporeal circuit. Instead of drawing blood into a static bag, blood is continuously cycled out of the body through an automated cell separator and back into the donor's circulation. High-speed rotation inside the centrifugal chamber forces blood to stratify by density. Heavy red cells push outward. Plasma settles inside. The system isolates the middle platelet-rich buffy coat into a collection bag, while rerouting the remaining red cells and plasma back to the donor. Removing blood from the body triggers an immediate coagulation response. To prevent the circuit tubing from clotting, anticoagulant CitrateDextroseFormulaA is continuously metered into the blood as it leaves the arm. This molecular animation demonstrates the mechanism of citrate chelation. The citrate molecules bind directly to free ionized calcium in the blood. By neutralizing this calcium, the chemical chain reaction of the clotting cascade is halted. This process carries a physiological cost. As the anticoagulated blood is returned, the citrate enters the donor's systemic circulation. This temporarily chelates the donor's own calcium, causing transient hypocalcemia, often felt as a metallic taste or tingling in the lips. The procedure also filters out specific white blood cells. To ensure long-term donor wellness, High-frequency donors undergo routine clinical monitoring to detect CD4+ T-cell lymphopenia, a progressive drop in immune cells caused by frequent extraction. When calibrated correctly, this fluid dynamic loop achieves remarkable efficiency. The system harvests up to 3 therapeutic units of platelets while fully preserving the donor's oxygen-carrying red cell volume. The efficiency gains of apheresis reshape transfusion economics. Pooling a single therapeutic dose of platelets requires 6 traditional whole blood donations. A single automated apheresis session produces up to 3 full therapeutic units from one individual. That scaling is critical. Depending on the severity of the treatment, a single marrow transplant recipient can require up to 120 units of platelets to survive the recovery phase. Utilizing apheresis-derived units solves a secondary clinical problem. By extracting highly concentrated volumes from a single donor, hospitals dramatically minimize the recipient's exposure to multiple foreign human leukocyte antigens, reducing the risk of an adverse immune response. Every parameter of the extraction, from the donor's cardiovascular fitness to the precise rotational speed of the centrifuge, exists to preserve this complex structural morphology. Donating platelets is a direct biological transfer of life-sustaining cellular material from a healthy donor to a critically ill recipient. Safely extracting the mechanics of the coagulation cascade remains a vital, irreplaceable link in modern survival.